Alrighty, moving on from where we were. What we had just talked about was the sums of forces and how to solve these problems in general. Now what I'm going to give you is a little bit more tricky of a problem, not due to difficulty, but just simply because it's in a different layout than anything that we had done. Right, let's say that now, this time, we've got an incline. Inclines always make everything a little bit more tricky. So let's say we have a 30-degree incline. We've got a box resting on that 30-degree incline. Now, to make our lives easier, we are going to assume no friction. Now, I know this is not an accurate assumption, but we haven't talked about friction yet in this type of a case, so I would rather start with an easy case rather than a hard case involving friction. So, let's say that we've got a rope tethered up to a wall up here. Alright, let's say the mass of that box is 25 kilograms. Now, if I were asking you two different problems here. Part A. What is the tension in the rope? And part B, what would be the acceleration if the rope snapped? Okay, two questions that would be interesting to know the answer to here. Okay, so now first thing that I want to talk about before I even go into what the problem is what a tension is. Tension is always a stretch or a pull. In other words, if you were to take a shoelace, hand one end to a friend and hold on to the other end, you would be able to pull that friend towards you, but you would never be able to actually push that friend away using that shoelace. A tension is something that can only act in a pulling manner. So when I'm drawing forces that are due to tensions, I would assume that this is going to pull up on the wall. I'm sorry, pull up on the box. I apologize. Okay? So, I'm going to start with my free body diagram here. There's my box. Right now, the tension is obviously going to be going in the same direction as the rope. Just like if you had a rope and you were pulling on it in one direction, whatever direction that rope is in, that is the direction that you can pull. You cannot pull at any angles other than what your rope is already set. So as soon as I see the rope, I see the direction, I know everything that's going on here. And I know that this rope cannot be pushing on the box, so it must be therefore pulling. Alright, now, the next obvious one. We worked with this to a deep extent last year. Weight always acts straight down, and weight is going to be the mass times gravity. Now, here's where things get tricky. Instead of the normal force being straight up and making our lives easy now, instead, the normal force is going to be normal to that surface. So right now, I've got my free body diagram. There's no friction involved, so everything should be pretty much good to go. Now, there's a couple of different ways of skinning this cat right here. There's not exactly one set way that's better than any others, but this one will definitely work for what you need. Right? What I like to do is rotate the reference frame. Okay? Because right now, I've got one that is acting entirely in the y direction. I've got one that is acting partially in the x, partially in the y, or in other words, I've got one that has an x component here and a y component here. I've got another one that has an x component here and a y component here. So, I can sit here and break this into xy components, this into xy components, and this one is already in y. That's an easy way of doing it. Okay? It's simple, it's to the point, and you're not going to run into many problems. If you like doing it this way, do it this way. It may take you another extra step in comparison to what I'm doing, but please, if this is something you understand, if this is something you know, if this is something you can use, please use it. Right? But what I like to do instead is what I call rotating the reference frame. Now I'm going to eliminate a little bit of the wording here just so that I can try to select this box. Alright, good. Now, if I rotate the reference frame, notice what's going to happen here. I take this box, and I twist it by 30 degrees to the right. Now, look at what I did here. I just made my life a little bit simpler. Instead of having an X component and a Y component, I now have just an X. I've got my tension acting only in the X. Instead of having an X component and a Y component, now my normal force is acting only in the Y. So, I now have eliminated I've made one math problem instead of two here. I now have an X component of my weight and a Y component of my weight. Alright. So by doing this, I can actually eliminate the fact that I have to break this into components and this into components, split this into components, and just leave the other two as they are. Okay? So, let me start with sum of the forces in the X. Now, I'm assuming something. If this rope is holding it, I'm assuming that it's not accelerating. In other words, it's not in motion. Therefore, the sum of the forces in the X direction is going to equal 0. Now, if I use my rotated reference frame here, I'm going to have my tension acting in the positive X direction, and I'm going to have my weight in the X direction acting in the negative X direction. Right. Now in this case here, my overall weight is going to be 25 times the acceleration due to gravity. So let me get my handy dandy calculator up here. Times 9.8, and that tells me that the overall weight of this is 245 newtons. Right now, I rotated this box by 30 degrees this way. So that means that this angle right here is going to be my 30-degree angle. So in order to find the cosine, in order to find the X component of it, it's going to be 245 times the sine of 30. So, sum of the forces in the X equals 0 equals tension minus 245 sine 30. It becomes a basic plug and chug in your calculator, and you can find exactly what the tension on that string is. Okay? Now, it turns out that if I'm not asked about the normal force, I'm not going to worry about finding the normal force. For right now, they don't ask anything about that normal force. So because of that, I'm just going to leave it go. Alright? Now, the acceleration. That's kind of interesting. Because basically what's happening now is if I were to draw a new free body diagram, let me just shrink this down so I still can fit this all on the same page. Basically what has just happened is now on my free body diagram, the tension of force is gone. I don't have a force in the X. I'm going to have my normal force, and I'm going to have my weight. Now it should be fairly obvious what direction this is going to go. There is no pull in the positive X direction, but there is a pull in the negative X direction. So in that regard, I should be able to tell that there's going to be an acceleration in this general direction. The acceleration is going to be down the slope or towards the left. Okay, so my sum of the forces in the x direction is going to equal the mass times the acceleration. Now, I know how much in the x direction the weight is pulling. I already figured that out right here. So that means that the mass times the acceleration is simply negative 245 sine 30. I plug in my mass, well I know my mass, and I can solve for the acceleration. Right? This should prepare you for the first homework assignment. The first homework assignment will be on the calendar regarding exactly how to do it. If you have any questions or problems, please let me know. I will be happy to help you out. I'll give you probably 2 days in class to work on it before we go into some in-class problems, some other things you're going to need to work on. But all in all, it should not be too difficult. Realistically, the concepts are not any tougher than anything that we've done before. The thing that is going to be different, and I'm going to remind you guys to do this because a couple of the problems are actually going to be significant if you do this. Do not round inside your problem. So, in other words, if I were to find out that the acceleration of some object was 6.66666 repeating meters per second squared. If you were to find that as your answer, and then you were to try to determine a force based upon that acceleration, if you were to just take 6.6 or 6.7 as your acceleration, you're going to end up with a significant rounding error in your end result answer. So if you have this as an intermediate step, I think all of you guys have TI-89s for in here, so please use the TI-89 storage feature and pull down the numbers rather than writing down new numbers each time or rounding every time. The more you round, the further and further off your end answer will be. Alright? So please, 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 especially the one that's talking about a solar yacht or a solar sailboat or something like that, do not round. Rounding is going to give you a significant error. Okay? Now give those homework problems a try and we'll see where we go. Best of luck to you and look for the next video when you're ready to learn about friction.